Have you ever looked up at a tapestry of stars and felt an unsettling thought? What if none of it is real? What if the entire universe, the planets, the galaxies, and even your own existence are nothing more than an elaborate cosmic illusion? This mind-bending concept isn't just science fiction anymore. It's called the simulation hypothesis, and it suggests our reality could be the programmed product of a superior intelligence. This notion of a simulated world might sound outlandish, but philosophers have wrestled with a similar idea for millennia. The ancient Greek philosopher Democritus proposed a startlingly simple idea. The universe and everything in it, including ourselves, is fundamentally made of tiny, indivisible particles he called atoms. Every sensation, every thought, every emotion could ultimately be explained by the complex interactions of these basic building blocks. This worldview, known as materialism, became the cornerstone of the scientific revolution, fueling centuries of breakthroughs in our understanding of the physical world. But even as materialism triumphed, a nagging question remained. How does consciousness arise from mere matter? How can the arrangement of atoms give rise to the rich inner world of thoughts, feelings, and subjective experience? This is perhaps the greatest unsolved mystery in science. Centuries before Democritus, another Greek philosopher named Plato proposed a radically different view of reality. He argued that the ever-changing material world we perceive is but a shadow of a truer, more perfect reality, a realm of eternal and unchanging forms. Forms are like abstract blueprints or templates that give rise to the objects and concepts we see in the physical world. To Plato, our senses deceive us, and our minds, capable of grasping these forms, hold the key to understanding the real world that lies beyond our perception. Plato's most famous metaphor is the allegory of the cave. Imagine prisoners imprisoned in a cave since birth, chained so they can only see the shadows cast on the wall by a fire behind them. For the prisoners, the shadows are all they know of reality. Plato argued that we are like those prisoners, mistaking the fleeting appearances of the material world for the true and ultimate reality. Does this sound familiar? The idea of a deeper, hidden reality from which our own is derived is remarkably similar to the concept of a simulation. If our universe is a computer program, then Plato's forms could be seen as akin to the original code and our material world its imperfect projection. The question then becomes, could we, as Plato suggests, ever break free of our cave and perceive the true nature of our simulated existence? Quantum revolution changes everything. If the ideas of Democritus and Plato left you with a sense of what reality might be, the discoveries of quantum physics in the early 20th century shattered those notions completely. Scientists delving into the world of the very small found that the universe is far stranger and more unpredictable than anyone could have imagined. The idea that atoms are the indivisible building blocks of matter? Gone. Experiments revealed that particles like electrons can behave as both solid objects and waves of energy. Imagine trying to visualize that. Even stranger, these particles seem to exist in a state of superposition, existing in multiple places or states at once until they are observed. Here's where things get mind-bending. The famous double-slit experiment shows this in action. When scientists fire tiny particles, one at a time, through two narrow slits onto a detector screen, you might expect to see two distinct lines where the particles land. But that's not what happens. Instead, an interference pattern emerges, a pattern that looks like what you'd get if a wave of water passed through both slits at once. This means each single particle must somehow be passing through both slits simultaneously, as if it were a wave. But here's the kicker. When scientists place a detector to see which slit the particle goes through, the interference pattern vanishes. The particles now behave like little billiard balls, landing in two distinct clumps. The mere act of observation seems to collapse the wave of possibilities into a single definite reality. But how is that possible? What determines when and how that collapse happens? And most importantly, what or who qualifies as the observer? These unsettling questions are still far from being answered. Quantum physics forces us to confront the limits of our materialistic worldview. If the most fundamental components of the universe exist as shimmering probabilities rather than solid objects, and if the observer plays a crucial role in shaping that reality, Could that imply a similar dynamic operating on the grand scale of the entire universe? Does it hint at a great simulator, and us as the observers whose perception solidifies a world from a multitude of possible ones? Could the perplexing behavior we see at the smallest scales of the universe imply a grand cosmic illusion? If reality is fundamentally observer-dependent, who or what is the observer at the level of the entire universe? Is it us? Or are we, like pixels in a cosmic video game, just players in a simulation designed by a vastly superior intelligence? We don't yet have the answers, but the questions themselves are as unsettling as they are thrilling. Sidebar: Schrödinger's cat. Erwin Schrödinger, one of the pioneers of quantum physics, devised a famous thought experiment that highlights the bizarre implications of the observer effect. Imagine a cat trapped in a box with a vial of poison, set to break open by a mechanism triggered by a random quantum event. According to quantum theory, before the box is opened, the cat exists in a superposition, both dead and alive at the same time. Only when we open the box and observe the cat does its state become defined, either tragically dead or miraculously alive. Schrödinger intended this to show the absurdity of applying quantum ideas to everyday objects. But what if, on the grandest scale, our entire universe is like Schrödinger's box? Does reality only snap into focus when an observer of sufficient scale and intelligence perceives it? Who or what might that observer be? Scientific evidence. The Big Bang and simulation code. The universe as we know it, the billions of galaxies, the trillions of stars, the swirling planets teeming with life, perhaps, all of it seemingly erupted into being from a single, infinitely dense point nearly 14 billion years ago. This cataclysmic event, known as the Big Bang, marks the beginning of space and time as we understand them. But how did something spring forth from absolutely nothing? Traditionally, materialists have grappled with this question. The idea of a universe without a cause, a creation without a creator, strains our everyday logic. Yet, the Big Bang model, supported by overwhelming observational evidence, seems to demand just that. The simulation hypothesis offers a different perspective. Imagine the universe as a sophisticated computer program. When a programmer launches that program, it begins to execute its internal code, generating a dynamic and complex virtual world. The Big Bang could be analogous to that boot-up moment, the instant that the simulation's underlying code sprang into action. Let's unpack this idea. In a computer simulation, the fundamental stuff of reality is information, not matter. Think about a video game. The characters, objects, and environments you see on the screen look convincingly solid. Yet, they're ultimately made from invisible bits of code. Could the same hold true for our universe? Could everything we experience be a grand illusion generated by an underlying universal code? Quantization and digital realities. For centuries, physicists assumed that the fundamental properties of the universe, things like energy, space, and time, were continuous. Picture energy smoothly ramping up like the volume of a radio, or space as an infinitely divisible sheet. What scientists discovered in the early 20th century shattered that view. It turns out that energy doesn't exist in a smooth continuum. Instead, it comes in discrete packets called quanta. An atom can't possess just any amount of energy, only specific levels, like steps on a staircase, rather than a smooth ramp. This unsettling discovery, the birth of quantum physics, revealed a surprising chunkiness at the heart of reality. The digital analogy becomes even stronger when we consider space and time. Could they too be made up of tiny, indivisible units, like the pixels on a computer screen? While this is still debated, leading theories of physics suggest that both space-time might be quantized at incredibly small scales. If true, this has profound implications for the simulation hypothesis. Imagine zooming in on the fabric of a computer-generated world. At first, everything looks continuous and smooth, but as you zoom further, you eventually hit a limit. Individual pixels become visible. Our universe could operate the same way. The familiar world of continuous space and time might just be a convincing illusion. Zooming in to the smallest possible scale may reveal a pixelated structure. This would align eerily well with the notion that our universe is a sophisticated simulation rendered on an impossibly powerful cosmic computer. Speed of light as processing limit. Nothing travels faster than the speed of light in a vacuum. This seemingly arbitrary limit isn't just some inconvenient rule of the universe, it's woven into the very fabric of reality. Albert Einstein's theories of relativity demonstrated that the faster an object moves, the more massive it becomes, the more time slows down for it, and the more space distorts around it. At the speed of light, these effects become infinite, making that barrier effectively impossible to break. But what determines this absolute speed limit? Traditional physical explanations point to fundamental properties of electromagnetism and the way space-time works. The simulation hypothesis offers another possible explanation. The speed of light could represent the processing limit of the cosmic computer running the simulation. Let's use a familiar analogy. In a video game, the complexity of the environment and the number of actions occurring simultaneously are constrained by the computing power available. If the processor is overloaded, the game slows down, graphics may glitch, and responsiveness suffers. Similarly, the speed of light might represent the maximum render speed of the universal simulation. Exceeding it would cause the simulation itself to lag, resulting in the kinds of relativistic effects we observe in our real-world physics. Quantum entanglement and non-locality. If quantum mechanics has taught us anything, it's that the universe is far stranger and more deeply interconnected than we ever imagined. Consider the phenomenon known as quantum entanglement. When two particles, like photons, light particles, or electrons, become entangled, they remain mysteriously linked even when separated by vast distances. Measuring the properties of one entangled particle instantly determines the properties of its entangled partner, regardless of how far apart they are. This seems to violate Einstein's cosmic speed limit. Information about the state of one particle seems to travel to its partner instantaneously. Einstein famously dismissed this as spooky action at a distance, believing there must be some hidden variables at work. But decades of experiments have shown that this spooky connection is real. It seems like entangled particles somehow exist as a unified system, defying our usual notions of space and time. The simulation hypothesis can offer some insight into this mystery. In a computer simulation, geographically distant objects within the virtual world can be instantaneously connected via the simulation's underlying code. The visible distance within the game doesn't reflect the deeper connections that exist at the programming level. Could quantum entanglement be hinting at a similar structure to our own universe? Some physicists theorize that entangled particles might be connected by shortcuts outside the conventional dimensions of space-time, like theoretical tunnels through the fabric of reality known as wormholes. If our universe is a simulation, such shortcuts could be written directly into the underlying code, providing an explanation for the seemingly impossible behavior we observe in quantum entanglement experiments. EA raises fascinating questions about the nature of the simulation and its creators. If there's a speed limit imposed from outside our simulated universe, it implies a higher-level reality where those laws don't apply, a reality where our simulators reside. Consciousness. The glitch or the purpose? Perhaps the greatest challenge to the simulation hypothesis is explaining consciousness. How can subjective experiences, the feeling of pain, the taste of a ripe strawberry, the awe of gazing up at the starry sky, arise from mere code, no matter how complex? Many materialists would argue that consciousness is ultimately an illusion, a complex product of biological processes that give us the sensation of being more than programmed automatons. The simulation hypothesis, however, offers multiple intriguing possibilities. Perhaps consciousness is not merely an emergent property of the simulation, but a foundational one. Consider this. If we're capable of creating simulations with ever-increasing levels of sophistication, including simulations where characters develop some level of awareness, isn't it plausible that our own consciousness is the result of a similar process? Maybe we are the simulated entities within a grander simulation. Alternatively, maybe consciousness is the purpose behind the simulation. Perhaps the simulators are interested in observing how consciousness develops and evolves within a controlled environment. This raises profound questions about our own role as participants. Are we merely objects of study, or does our simulated consciousness possess the same kind of value and agency as it would in a non-simulated reality? If so, do we have any responsibilities towards our creators? Of course, there's the possibility that the type of consciousness we experience is inherently incompatible with the simulation scenario. Maybe it's a property unique to the base reality outside any simulation. If this is the case, then the simulation hypothesis might fall apart under its own weight. However, the very fact that we can conceive of the idea of simulation, question the nature of reality, and experience wonder and awe at our own existence suggests that there's something exceptional and perhaps transcendent about the human mind. Potential flaws and counterarguments. It would be intellectually dishonest to present the simulation hypothesis as a slam-dunk explanation for the nature of reality. Like any audacious theory, it has its detractors and raises some legitimate concerns. Here are a few key ones it's important to address. The complexity argument. Critics argue that the computing power and energy required to simulate a universe as complex as our own, with conscious beings inside of it, are simply unimaginable. While the resource demands would be staggering, proponents of the simulation hypothesis point out that it just depends on how advanced the simulators and their technology might be. If they exist in a reality far beyond the limitations of our own, simulating our universe could be a relatively trivial task for them. The why bother argument. Skeptics question what the motivation for running such an enormous and detailed simulation would be. Pure curiosity, scientific study, perhaps even entertainment? The truth is, we simply can't fathom the aims of beings vastly more intelligent and technologically advanced than ourselves. Like ants pondering the motivations of humans building an ant farm, we may not be equipped to grasp the full picture. The glitch test. Wouldn't we notice glitches or inconsistencies in reality if it were a simulation? This objection hinges on the assumption that the simulation would be imperfect. However, a simulation sophisticated enough to fool its inhabitants into believing their reality is fundamental might also be flawless in its execution. Or perhaps those flaws do exist, and the unexplained phenomena we discover in physics are subtle hints at the underlying code. Searching for the simulation's edge. While the simulation hypothesis might seem untestable, confined to the realm of philosophical speculation, physicists are actively exploring potential ways to uncover glitches or artifacts that could reveal the true nature of our simulated reality. Here are a few theoretical possibilities. Limitations of resolution. If space-time is quantized, there might be a fundamental pixel size to the universe. Detecting this ultra-fine graininess would be exceedingly difficult due to its incredibly small scale, but could be strong evidence for a simulated reality. Some physicists believe the existence of high-energy cosmic rays that seem to violate known energy limits might hint at such a resolution limit. Errors in the code. Like glitches in a video game, there could be moments where the rules of our simulated universe seem to break down momentarily. Careful study of anomalies in astronomy or particle physics might reveal such cracks in the facade of reality. Some potential candidates include strange alignment of distant space objects or particles that seem to pop in and out of existence, defying known laws of physics. Computational limits. If the simulation has limitations on processing power or storage, there might be observable consequences. Cosmologists propose that. Searching for a maximum level of complexity beyond which the universe simply doesn't generate new structures or phenomena could be a telltale sign. Similarly, if certain calculations about the behavior of the universe yield nonsensical results, like infinities, that could point towards limits imposed by the simulation. Philosophical implications. If we are indeed living within a simulation, it has profound implications for how we understand ourselves, the nature of existence, and even the concept of ethics and meaning. Here are just a few of the mind-bending questions that arise. Free will or pre-programmed? Does the existence of a simulation imply that our choices are predetermined, that we're merely following lines of code laid down by our simulators? Or does the simulation allow for enough complexity that genuine free will and agency can still exist within its boundaries? This question strikes at the heart of what it means to be human. Are we special? Do we hold any significance within this grand cosmic simulation, or are we merely insignificant blips within a vast computational experiment? If there are levels of simulation, simulations within simulations, does our value diminish with each level further down we are from the base reality? Purpose and meaning. If our universe is a manufactured construct, does that undermine any inherent meaning in our existence? Or perhaps the simulators have a grand purpose in mind for the simulation that we're unknowingly a part of. Our search for meaning might then become the search for our programming and the role we're meant to play within the simulation. Ethics and morality. How do our moral systems and ethical codes hold up within a simulated reality? If suffering is ultimately not real in the same way, does that alter how we view right and wrong? On the other hand, if our simulated experiences are just as vivid and meaningful to us as they would be in a base reality, then shouldn't our ethics reflect that? The ultimate mind-bending twist. The possibility that our universe is a meticulously crafted simulation has the power to reframe our entire perspective on reality. If the fundamental building blocks of existence are information rather than matter, it casts doubt on the naive realism most of us instinctively subscribe to. Our seemingly solid world might be no more substantial than a convincingly rendered video game environment. This idea has echoed throughout centuries of philosophical questioning. Are we mere shadows dancing on the wall of Plato's cave? Are our minds, with their rich inner worlds of experience, the only fundamental reality, shaping an external world that may ultimately be illusory? The simulation hypothesis takes these age-old questions and supercharges them with the latest discoveries at the frontiers of modern physics. Whether or not the simulation hypothesis turns out to be correct, simply entertaining the possibility offers a profound opportunity for intellectual and even spiritual growth. It forces us to confront the limits of our knowledge, to marvel at the potential complexity of the universe, and to question our place within it. Even if we never find definitive proof that we're living within a simulation, the very act of pondering this mind-blowing possibility sparks wonder and ignites a sense of awe. Perhaps the most vital ingredients for fueling continued scientific exploration and the relentless pursuit of understanding the true nature of existence. The spark of awe. Whether we are the players or the programmed, the explorers or the experiment, living within a simulation presents a powerful reminder. There might be layers to reality far beyond our current comprehension. The world we experience may be just one dimension of a far more complex and multifaceted existence. Perhaps the true purpose of the simulation, if simulation it is, lies not in providing answers, but in the asking of the questions themselves. The relentless pursuit of knowledge, the drive to peek behind the curtain of reality, and the awe we feel when confronted with the profound mysteries of the universe. Could these be the very reasons our simulation exists? The simulation hypothesis, whether ultimately true or not, serves as a testament to the boundless power of the human mind. Our capacity to conceive of such a reality is itself proof of our remarkable potential. It challenges us to embrace skepticism, to think critically, and to always keep an open mind to the possibility that reality is far more extraordinary and awe-inspiring than we could ever fully grasp. And so, the great debate continues. Materialism, idealism, or something else entirely? The simulation hypothesis adds a 21st century twist to the ancient quest to decipher the true nature of existence. This journey of discovery, with all its twists, turns, and potentially mind-blowing revelations, is far from over. The ultimate thrill comes not in knowing for certain, but in the endless wonder of exploring the cosmic mystery we find ourselves a part of. The double-slit enigma. The double-slit experiment is widely considered one of the most beautiful and profoundly baffling experiments in all of physics. It reveals a fundamental truth about the nature of reality that shakes our everyday assumptions to the core. The act of observation seems to play a crucial role in determining the behavior of the building blocks of the universe. Let's break it down. Imagine firing tiny particles, like electrons, through two narrow slits in a barrier. On the other side of the barrier is a detector screen. If electrons behaved simply like solid little balls, you'd expect to see two distinct bands of hits on the screen, corresponding to where the particles traveled through each slit. But that's not what happens. Instead, you observe an interference pattern, a series of bright and dark bands, much like the pattern you'd get if a wave of water passed through the two slits simultaneously. This pattern arises because the waves passing through each slit interact, creating zones of amplification and cancellation. The mind-twisting implication is that each single electron seems to be passing through both slits at the same time, like a wave, and interfering with itself. Yet, when it hits the detector screen, it registers as a single particle. How can an electron be both a wave and a particle simultaneously? The mystery deepens. When scientists place a detector near the slits to see which path the electron takes, something remarkable happens. The interference pattern vanishes. The electrons now behave like those little billiard balls, leaving two distinct clumps on the detector screen. The very act of observation seems to collapse the wave of potential possibilities into a single definite outcome. This is the core of the observer effect, and it has profound implications for the simulation hypothesis. Could it be that the universe, at its most fundamental level, is a vast potential wave of possible states or events? Only when an observer, whether a conscious being or simply a measuring device, interacts with the system, does this wave collapse into a concrete reality. If that's the case, could the simulators be the ultimate observers that solidify our universe into existence? The simulation hypothesis isn't just about mind-bending theories and speculations about computer code. Some of the most compelling hints that we might be living in a simulated reality come from the seemingly solid world around us. Scientific experiments designed to probe the fundamental nature of reality are yielding increasingly bizarre results, suggesting that the fabric of the universe might be far stranger than we ever imagined. Could it be that unexplained glitches, anomalies in the laws of physics, or even seemingly impossible events hold clues to the simulated nature of our existence? Are these the cracks where the simulated world starts to show its true nature, or even deliberate signals left by our simulators? Let's turn our focus to the unexpected, the unexplained, and the downright strange. In this next part of our journey, we'll explore the fringes of the known, where reality seems to bend, break, and perhaps even reveal its programmed nature. The mind-bending eraser. If the double-slit experiment challenges our understanding of the present, the delayed choice quantum eraser experiment forces us to re-examine the very nature of the past. It's an even more complex variation on the double-slit setup, but bears with me as the implications for the simulation hypothesis are profound. In this experiment, scientists introduce an additional twist after the particle has already passed through the slits. They use a special crystal that splits the light from the particle into two entangled photons, sending them in different directions. Now, by manipulating one of these entangled photons, scientists can determine whether its entangled twin displays an interference pattern, wave-like behavior, or not, even though that twin should have already hit the detector screen well before this manipulation occurs. In essence, this experiment suggests that a decision made in the present can retroactively affect the behavior of a particle in the past. The very act of obtaining information about a particle's path, even after it should have already taken a set path, seems to erase its earlier wave-like history. It raises deep questions about the flow of time, causality, and whether the past is truly fixed or only solidifies when observed. How does this relate to the simulation hypothesis? Imagine a cosmic simulation where, due to processing optimization, the specific details of a past event aren't rendered until they're directly observed or recorded. It's like a video game that doesn't bother generating the background scenery until a player turns their head to look in that direction. The delayed choice experiment suggests our universe might behave similarly on a fundamental level. Could this be evidence for a simulation that conserves its computational resources? Macroscopic quantum weirdness. Traditionally, the bizarre behaviors observed in the quantum realm, things like superposition and entanglement, were thought to be confined to the world of the very small. Atoms, electrons, and photons could exist in multiple states or places at once, seemingly defying our classical notions of how reality should operate. But what if the line between the quantum world and our own macroscopic reality isn't as rigid as we once believed? Increasingly, experiments are pushing those boundaries with startling results. Scientists have managed to coax larger and larger objects, like collections of atoms or even tiny visible mirrors, into exhibiting quantum behaviors. Consider the idea of superposition. In the quantum world, a particle can exist in multiple states simultaneously. Think of it like a coin that's both heads and tails at the same time. While this seems impossible for everyday objects, experiments hint that under very specific conditions, even larger objects might be capable of existing in a superposition of states. How does this challenge our understanding of the simulation hypothesis? If quantum weirdness isn't limited by scale and even the stuff our real world is made of could exist in nebulous states of potential until observed, isn't that eerily similar to how a digital simulation might function? Perhaps the simulation doesn't need to render our entire world in full detail all the time. Maybe some objects and events flicker in and out of definite existence, solidifying only when they interact with a conscious observer. Glitch in the Matrix? We've explored the theoretical arguments and scientific experiments that hint at the possibility of our reality being a sophisticated simulation. But what about the instances where the simulation seems to glitch or malfunction, revealing the seams in the fabric of reality? Throughout history, there have been countless accounts of seemingly inexplicable phenomena, strange coincidences that defy all odds, vanishings and reappearances that challenge our understanding of space and time, and bizarre distortions of reality that seem to bend the very laws of physics. Consider a few examples. People who inexplicably disappear without a trace, their belongings left behind as if they simply blinked out of existence. Objects seeming to teleport short distances or appear out of thin air, defying what we know about the conservation of matter. Clusters of people reporting vivid shared dreams or memories of events that never happened, suggesting a potential bleed-through between simulated realities. While skeptics might dismiss these as hoaxes, misperceptions, or rare statistical anomalies, their sheer strangeness begs the question: could they represent moments when the underlying code of our simulation hit an error or exposed a limitation? If our reality is the product of programming, isn't it plausible that there might be occasional bugs in the system? Of course, it's crucial to emphasize that these stories don't constitute proof of a simulated universe. However, they ignite a sense of profound unease about the true nature of existence. They force us to question the limits of our perception and what we consider impossible. Could these glitches be tantalizing clues, hinting at a deeper level of reality hidden beneath the surface? Consciousness, glitch or purpose? Perhaps the most profound challenge to the simulation hypothesis is also its greatest potential source of support: the mystery of consciousness. How does subjective experience, the feeling of being you, the inner world of thoughts, emotions, and perceptions, arise from the seemingly insentient matter of the brain? Materialists argue that consciousness, despite its complexity, is ultimately nothing more than the emergent result of neurons firing and complex biological processes. Yet, no amount of detailed understanding of the physical brain has brought us any closer to explaining how the qualitative feeling of being alive emerges. This hard problem of consciousness poses a serious challenge to any purely materialistic worldview. The simulation hypothesis, however, offers intriguing possibilities. If reality is fundamentally made of information, not matter, then perhaps consciousness itself is a pattern of information processing rather than the result of it. This opens several fascinating avenues of exploration. Simulated sentience. Could a sufficiently complex simulation create the illusion of consciousness, giving rise to entities that believe themselves to be feeling, self-aware beings, even though they're ultimately made from lines of code? If so, what does this say about our own sense of self and the experience we call real? Fundamental consciousness. Perhaps consciousness isn't an emergent property of complex systems, but a fundamental component of reality itself. In this view, the simulation might exist precisely to provide a framework for consciousness to interact with, to experience constraints and limitations, and ultimately, to evolve and grow. The question of consciousness casts a long philosophical shadow over the simulation hypothesis. If consciousness can indeed be simulated, what does this tell us about our own nature as beings capable of awareness, feeling, and self-reflection? And if consciousness is fundamental, how might that shape our understanding of the simulation and its purpose? Free will versus pre-programmed fate. If we exist within a simulated reality, the question of free will becomes fraught with dizzying implications. On the one hand, if our universe is nothing more than an incredibly complex computer program, the idea of true freedom of choice seems to crumble. Wouldn't every action, every decision, ultimately be predetermined by the underlying code that governs the simulation, Like puppets controlled by the strings of our programming, we might act with the illusion of autonomy, yet ultimately, every step of our journey would have been laid out in advance by our simulators. This echoes the deterministic view held by some materialists who argue that the laws of physics and the initial conditions of the universe dictate every single event that unfolds within it, leaving no room for genuine free will. But could there be wiggle room within a simulation? Consider this. Even complex video games offer players some degree of agency. While the overarching rules and boundaries of the game world are fixed, there's still a spectrum of choices available within those constraints. A sufficiently advanced simulation might offer similar latitude, allowing its simulated inhabitants the perception of free will, while ultimately being bound by the grander parameters set forth by its creators. Furthermore, if consciousness itself is an element of the simulation's code, could there be potential for emergent behavior, even choice, that the simulators themselves did not directly program? This leaves open the tantalizing possibility that even within a fabricated reality, true freedom might still find a way to express itself. Simulated suffering and the ethics question. If the simulation hypothesis is correct, it fundamentally alters our ethical calculus. Consider the existence of pain and suffering within a simulated reality. If these experiences are not real in the same way they are in the simulator's base reality, does their ethical weight diminish? Some might argue that simulated pain and suffering, devoid of real biological consequences, matter less. After all, no physical harm befalls a conscious being in the base reality. Yet, this viewpoint risks devaluing the simulated beings and their experiences. The counter-argument is potent. If simulated pain feels indistinguishable from real pain to the entity experiencing it, shouldn't our ethical systems still apply within the realm of the simulation? After all, the simulation can create intense, vivid experiences of joy, love, beauty, and wonder. If these hold value, shouldn't suffering hold its negative counterpart? The simulation hypothesis forces us to confront the potential sentience embedded within what we might otherwise dismiss as just a game. If our entertainment comes at the cost of programmed but nonetheless real feeling suffering, the lines of morality begin to blur in deeply troubling ways. Moreover, could the simulation be designed as an elaborate experiment in ethics? Perhaps the simulators are interested in how moral codes develop and function within a controlled environment. This adds yet another layer of complexity to our own ethical considerations. We become not only moral agents within the simulation, but potential subjects of study by beings who exist beyond our comprehension. Purpose in a programmed existence. The possibility of living inside a simulation upends our traditional frameworks for finding meaning. If there exist simulators, beings who have created and control the reality we inhabit, then the burning existential question becomes, why? What is the purpose of the simulation, and what role do we play within it? Let's consider a few possibilities. Scientific inquiry. Our simulated universe could be a grand experiment, designed to observe how life develops, how consciousness evolves, or how societies function under specific conditions. In this scenario, we might be objects of study, our struggles and triumphs little more than data points for the simulators. Research. Entertainment or art. Perhaps our existence is a source of entertainment for our simulators, a complex story playing out for their amusement. This raises unsettling questions about whether our experiences of love, loss, joy, and pain are trivialized if they exist solely to entertain beings on a higher plane of reality. Or maybe the simulation holds purpose as an elaborate form of art, with meaning we are incapable of fully grasping. Self-understanding. Could the simulators have created our simulated reality as a way to better understand themselves? By setting up a universe with different rules or limitations than their own, they might gain insights into fundamental aspects of existence that would otherwise be obscured to them. The ultimate search. Perhaps the most profound possibility is that the very act of seeking to understand our place in the simulation is the core purpose of its existence. The questions we ask, the drive to unravel the true nature of reality, and the never-ending quest for knowledge might be the grand objective our simulators intended all along. The simulation hypothesis transforms the search for meaning from a purely personal endeavor to a cosmic mystery. The answers we seek may not lie in the simulated world around us, but in understanding the minds behind its creation. If we are programmed beings, then finding purpose means decoding the intentions of our programmers and our role in their grand design. Searching for the glitch. The potential evidence for the simulation hypothesis isn't confined to philosophy and thought experiments. Physicists are actively exploring ways that the true nature of reality might reveal itself through detectable anomalies, imperfections in the code that betray the underlying artificiality of our universe. Let's consider a few of the theoretical glitches researchers are looking for. Resolution limits. If space-time is quantized, there might be a fundamental pixel size to the universe. Detecting this ultra-fine graininess would be exceedingly difficult due to its incredibly small scale, but could be strong evidence for a simulated reality. Some physicists believe anomalies like unexpected high-energy cosmic rays might hint at such a resolution limit. Processing errors. Like glitches in a video game, there could be moments where the rules of our simulated universe seem to break down momentarily. Careful study of unusual astronomical phenomena or discrepancies in the behavior of particles at the subatomic level might reveal such cracks in the facade of reality. Computational limits. If the simulation has limitations on processing power or storage, there might be observable consequences. Cosmologists propose that searching for a maximum level of complexity, beyond which the universe simply doesn't generate new structures or phenomena, could be a telltale sign. Additionally, if certain mathematical calculations about the behavior of the universe yield nonsensical results, like infinities, that could point towards limits imposed by the simulation. It's crucial to emphasize that none of these are definitive proof, but they offer tantalizing avenues for future scientific investigation. The very act of physicists taking the simulation hypothesis seriously enough to develop testable predictions is a testament to how it has sparked a sense of wonder and a renewed drive to push the boundaries of our understanding of the cosmos. Limitations of proving a negative. While the idea of finding concrete evidence of the simulation is thrilling, there's a fundamental obstacle: proving a negative. How can we definitively prove that we don't live in a simulation, when a sufficiently advanced simulation could be indistinguishable from reality itself? Consider the analogy of a character within a hyper-realistic video game. Unless the game glitches or reveals its internal coding in some obvious way, how could that character ever definitively know they weren't living in the real world? They might observe patterns and consistencies within their environment and develop scientific models to explain them, yet the underlying artificial nature of their existence could still remain hidden. The same challenge applies to our own attempts to prove or disprove the simulation hypothesis. No matter how detailed our understanding of physics becomes, there's always the possibility that our simulators have programmed in undetectable safeguards to maintain the illusion. A frustrating limitation, perhaps, but one that forces us to be intellectually honest about the boundaries of scientific inquiry. This, however, doesn't invalidate the simulation hypothesis entirely. The inability to definitively disprove it, ironically, strengthens the idea. It highlights the profound limitations of our knowledge and underscores how even our most advanced scientific tools might be incapable of revealing the ultimate nature of reality. Counter-arguments and flaws. While the simulation hypothesis is tantalizing, it's crucial to address the legitimate counter-arguments and potential flaws in the idea. Skepticism fuels scientific inquiry, and by examining the weaknesses of the hypothesis, we can refine it and potentially pave the way for even more intriguing lines of exploration. Let's delve into a few of the major objections. The complexity argument. Critics argue that the computing power and energy required to simulate a universe as complex as our own, with conscious beings inside of it, are simply unimaginable. While the resource demands would be staggering, proponents of the simulation hypothesis point out that it just depends on how advanced the simulators and their technology might be. If they exist in a reality far beyond the limitations of our own, simulating our universe could be a relatively trivial task for them. The why bother argument. Skeptics question what the motivation for running such an enormous and detailed simulation would be. Pure curiosity? Scientific study? Perhaps even entertainment? The truth is, we simply can't fathom the aims of beings vastly more intelligent and technologically advanced than ourselves. Like ants pondering the motivations of humans building an ant farm, we may not be equipped to grasp the full picture. The lack of a better model. Currently, the simulation hypothesis, while mind-bending, doesn't offer a more precise explanatory model for the universe than existing scientific theories. For many, this lack of a concrete